Hello, this is Nick of Time. Welcome to this 7th talk in this series. We're going to be continue to talk about special relativity, specifically about time dilation, and we'll get into the topic of the famous twin paradox. For two inertial clocks, A and B, whatever special relativity time dilation effect occurs, for A versus B, the same special relativity time dilation effect have to occur for B versus A. As you see, I'm abbreviating time dilation with TD. So time dilation has to be symmetric between the two inertial clocks that are involved. Why is that? Well, both the relativity principle and special relativity assert that all inertial frames are indistinguishable. But if we had different effects for time dilation between A and B versus B and A, then they would be distinguishable. In fact, it would imply a hierarchy in terms of relative clock rates. In addition, special relativity time dilation is a function of relative velocity, which is the same for A to B as for B to A. If you have clocks A and B, and they're approaching each other with relative velocity 5 miles an hour, then the relative velocity for A approaching B is 5 miles an hour, and the relative velocity for B approaching A is 5 miles an hour. And conversely, if they're separating by 5 miles an hour, it's going to be the same of A to B and B to A. So there are some consequences to that. And that's a key concept. If you forget it, you need to come back, look at the slide again, because it's going to underlie all that we talk about for a number of different topics. There are two interpretations of special relativity time dilation that are used by relativists. In fact, most relativists use both of them together. Not just that we have two different competing camps, camps supporting one interpretation and another supporting the second interpretation. Individuals use two contradictory interpretations. From what we talked about in the previous slide, one cannot interpret special relativity time dilation as claiming that clock A is accumulating proper time faster or slower than clock B. Proper time is just the amount of time that accumulates on a clock. Well, as Dingle put it, if you try to interpret special relativity times dilation as causing different proper time accumulation, one clock slower or faster than the other, then that requires that clock A works more slowly than clock B, and that clock B works more slowly than clock A, which it requires no superintelligence to see is impossible. That's a direct quote of Herbert Dingle. He was indeed a great physicist. Many other great physicists and critical thinkers agree with Dingle, and there I give a partial list, and earlier I gave a much, much longer list. So again, there are two interpretations of time dilation. We cannot have the invalid interpretation that special relativity time dilation describes physical clock slowing. or physical clock rate differences. But we can interpret time dilation as describing a just observed effect of A measuring or observing the B clock to be slow, and B measuring or observing the A clock to be slow. Unfortunately, relativists routinely use both interpretations, even though they're mutually exclusive and contradictory interpretations. And in addition, we've just clearly seen that one of those interpretations has to be invalid. Okay, what was the origin of that invalid interpretation that time dilation is talking about clock slowing as a function of relative velocity? Well, in the paper that Einstein had published in 1905, that was the seminal paper for defining special relativity. He had, after deriving special relativity time dilation, he made his twin paradox claim, which implied the invalid interpretation of time dilation. And when I'm talking about time dilation, I'm always talking about special relativity time dilation. That claim, namely that proper time accumulation rates change as a function of relative velocity. In the paper, right after he derives special relativity's time dilation equation, he says, from this, clearly referencing the time dilation equation, if two clocks are at rest in an inertial frame next to each other, and one clock makes a round trip, then it will return having accumulated less proper time than the clock that didn't move. Initially, that was called the clock paradox, and later the twin paradox. Let's just take a look at a picture of that claim. Basically, Einstein was talking about clocks, but if you think of human beings as biological clocks, their aging is like a clock, then it could be interpreted as follows. We have two twins there in the upper left. One is the astronaut twin. He gets into his rocket ship. He blasts off. He goes to some star system many light years away, and he doesn't stop there. He just turns around after filming everything and comes back. And you can see in the lower panels that the stay-at-home twin has aged greatly. But the traveling twin, because he was traveling so fast that the time dilation effect would be very, very large. He's aged hardly at all, but the twin that stayed at home, he must have aged about 50 years. That was the claim. And I guess it's this picture about the twin paradox claim and all the excitement about astronauts that's stayed in everyone's mind. So they think of the special relativity time dilation effect as causing differential clock rates or differential aging. Even though Einstein himself abandoned that interpretation, in effect, in 1916, it still lives on today. Okay, what was the initial reaction to Einstein's claim? Well, from 1905 to around 1919, many physicists objected to the twin paradox claim. They, in effect, said, how can a symmetric effect, the time dilation effect, produce an asymmetric effect? A difference in the proper time, the amount of proper time that was accumulated. Well, that question has never been reconciled with special relativity time dilation. However, the empirical data shows that clock rates are indeed a function of velocity. But that effect cannot be caused by special relativity's time dilation, because that's an invalid interpretation, as we discussed. So it must be caused by some other effect, such as a preferred frame theory, like the Lorentz ether theory. I've mentioned Lorentz ether theory, but I'm not endorsing the entire Lorentz ether theory, all of the details about the ether and whatnot. I'm just really talking about how the Lorentz ether theory treats time, namely clock retardation, where you have clock slowing as a function of velocity with respect to a single inertial frame and really a single physical entity, which in the details of the Lorentz ether theory is the medium, the ether rest frame. But it could be some other single entity, such as the local gravitational field rest frame. But a single preferred frame rather than special relativity's velocity with respect to each and every single inertial frame. So that's the basic discussion for today, and we'll continue to build on that and give more details in the next few sessions. Thank you very much for joining us, and hope that you'll come back next time. Thanks again.